Okay, so we have mentioned equatorial waves and how MJOs travel slower than the free waves throughout this series of podcasts on intraseasonal oscillations without actually looking at the wave structures or the equations. So I figured I'll make a few podcasts on convectively coupled equatorial waves. We use this terminology to explain why the MJO waves move slower than the free waves. We didn't even say what the free waves are. So we'll go through quickly this free waves and then look at convectively coupled waves from this nice paper by George Kiladis, Matthew Wheeler, Hartel, Straub, and Roundy, who are people who have been working on these MJO waves, equatorial waves, for a long time. The first original seminal paper on the equatorial wave comes from 1966 by Matsuno, who simplified the governing equations to shallow water equations on the equator in the tropics and found analytic solutions for the linearized equations. We will go through those and then add the complexities of convectively coupling them. So this is a nice paper from 2009. This paper here showed this nice figure of the time longitude section of symmetric and antisymmetric cloud top temperature data in Kelvin from Klaus, which is a product satellite data for 1992-93. In A, only threshold values less than 280 Kelvin are shown to emphasize convective activity. Remember that convective activity means deep, tall clouds, cold cloud top temperatures. So you pick a threshold for temperatures colder than a threshold, which is chosen here to be 280 Kelvin. Bottom map showing the symmetric component is obtained by averaging over 15 south, 15 north, and the antisymmetric component is obtained by subtracting the values at the northern latitudes from the corresponding southern latitudes. The boxed interval corresponds to Toga-Core intensive observation period, and the oval mark significant MJO event. So there are few MJO events here, and this is the box over which the Toga Tau core intensive observation period happened. So the symmetric part here, when averaged from 15 south to 15 north, cloud top temperatures are shown here, and the antisymmetric part as the difference between the northern and southern hemisphere is shown here. What do we do that? Basically we can take these and produce a time series and look at the spectral wave number frequency power spectrum of these symmetric and antisymmetric component of the Cloud Archive User Services temperature data. This is for July 1983 to June 2005. I'm mixing this data with this one because this nicely shows the symmetric and antisymmetric components, and this shows the spectrum, but they all should look the same. Okay, and the goal is to look for the equatorial waves in the cloud top temperature, and clearly you see that here. So you have zonal wave number here. When the wave propagate eastward, the wave number is positive. It's a convention. And when the waves propagate westward, the zonal wave number is negative. Frequency in this convention is assumed to be positive, but there is another system where the frequency is allowed to go negative, provides a much more complicated picture. But nonetheless, here frequency is in cycles per day for the symmetric Klaus TB spectrum, and obviously you have to go through other podcasts of mine in the tropical dynamics course, yeah, that's where I have all this equatorial wave material. So here I'm going to just do a very brief introduction. So what are we looking at here? Plotted is the ratio between raw TB power and the power in a smooth red noise background spectrum. So basically a statistical significance is shown as well, which we won't worry about. Dispersion curves for the Kelvin wave n equal 1, equatorial Rossby waves n equal 1 and 2, westward inertial gravity waves WIG for n equals 0, eastward inertial gravity waves and mixed Rossby gravity waves are plotted in equivalent depths of 8, 12, 25, 50 and 90 meters. Heavy solid boxes represent regions of wave number frequency filtering, which we'll come back to in a later section. So equivalent depth is basically a concept you have to get familiar with when you have a stratified system like the atmosphere, and you are filtering and extracting waves and trying to the data is from a real full four-dimensional atmospheric system which has this vertical stratification, and you're trying to extract wave spectrum out of it. Then equivalent depth is essentially a parameter that kind of allows you to match phase propagation speeds and so on to the actual data, filtered data. It's a parameter in the wave equation. We'll come back to that later on. Okay. So here you have the zero zonal wave number, around which you have westward propagating Rossby waves, and the energy of the spectrum is shown here, and the theoretical curves are shown in the lines. The contour interval is 0.1 and so on. So Kelvin waves have positive zonal number, zonal wave number, so they are eastward propagating, and you can see that they are, for different equivalent depths, they have constant slopes, so they are non-dispersive. If you do d omega dk, omega is the frequency, group speed is d omega dk, which is the speed with which energy moves, and phase speed is with which each waveform moves. So the packet of waveform moves with the group speed, and that corresponds to the energy propagation. So you can see that the Rossby numbers, Rossby waves, equatorial Rossby waves have a different slope of d omega dk here in the lower wave numbers than in the higher wave numbers. Okay, so the higher wave numbers d omega dk is positive, whereas here it's negative. So the longer waves, lower wave number means there are fewer wave numbers covering the planet, so they are long waves, and they have westward wave speed, and the shorter waves have eastward wave speed. And here you have westward inertial gravity waves and eastward inertial gravity waves, and you can see the slopes change sign here as well. And that's what you get for n equal 1, and we will see the equations in a minute that'll make it clear what we mean by 1. And the if you look at the anti-symmetric spectrum, you see the n equal to 2 westward and eastward inertial gravity waves. Okay, so this is westward inertial gravity waves, eastward inertial gravity waves here, and you also have mixed Rossby gravity waves here. So depending on the frequency and the wave number, they behave either as Rossby waves or gravity waves, so they have mixed Rossby gravity wave characteristics. And as I've said many times before, the terminology gravity wave and Rossby wave correspond to the restoring force. Rossby waves are related to the change in Coriolis effect with latitude, so that's the vorticity effect. As you remember, vorticity increases from the equator where it's 0 to the pole where it's maximum, and if you displace air parcel with a perturbation, then the vorticity conservation would pull it back, a restoring force which would produce waves. Okay, so that's the Mr. Rossby gravity waves. In case of gravity waves, of course, restoring force is gravity, and they move typically much faster, as you can see from the slopes here. Okay, so you can see the periods here: 30 days, 60 days, 3 days, 30 days, 60 days, 3 days. And this also shows that MJOs actually they have characteristics of Kelvin waves and Rossby waves, as we already talked about several times. But you can see that on the wave number frequency spectrum, they are down here in the 30-day period, and different from the free waves of Rossby and Kelvin, equatorial Rossby and Kelvin waves. That's why we kept saying that they move slower, and that's why we said they are convectively coupled. Okay, so how do the equations look? The equations we are not deriving here. You can take the full primitive equations and go through certain not so simple scaling arguments to produce the so-called shallow water equations for the deep tropics. When you say shallow water, obviously we're talking about the vertical structure being homogeneous. So water means it's incompressible fluid, so the horizontal length scale is much larger than the vertical scale. Using those equations and assuming that the Coriolis effect is a function of latitude in a linear sense, so beta times y is used. So these are called the beta plane equations. So you have the zonal momentum equation for a vertical mode L. So you have the acceleration term, the Coriolis term, and the pressure gradient term. That's the balance. In the meridional direction, you have the acceleration term, the Coriolis term, and the pressure gradient. And the continuity equation then becomes a function of horizontal divergence changing the geopotential height. So the acceleration term of the geopotential height is related to g times he, which is the equivalent depth that we mentioned here, and the horizontal divergence. So based on the horizontal divergence and convergence, there is a change in the geopotential height in the vertical because there is vertical motion. So this simple system then is solved using the waveform like this. So you pick meridional structure functions for u, v, and geopotential height with the waveform exponential ikx minus omega t, where k is the zonal wave number, x is the longitudinal coordinate x, and omega is the frequency time. So then the equations, when substituted with these waveforms, reduce to this oscillator equation. So d squared v dy squared plus this constant here, which is a function of frequency and zonal wave number. So this relates the frequency to the zonal wave number, times v, the meridional the meridional velocity, equal to 0. So solutions to this equation that decay away from the equator are well known, from which it follows that the constant part of the coefficient in the parenthesis here must satisfy this relation of the equivalent depth or height in the atmosphere. Coriolis df dy is basically beta, you already know that, and these terms here equal 2n plus 1, and n is the meridional God, I don't know why my computer does this. If somebody knows why my computer suddenly goes on the blink, please send me a message. So n equals 0, 1, and 2. So these are meridional modes. So how many zero crossings happen in the meridional direction. You don't want solutions growing infinitely with y. Remember, there is a y in this equation, boom, boom, somewhere. So for example, we have y in these equations. So we pick the equations that decay away from the equator, and we already kind of introduced the concept of turning latitudes and so on. So that relates to this. So we'll come back and look at the details of how the solutions look, and we will project these free waves onto the wave number frequency spectrum and see how the MJO related waves look almost like the free waves, with subtle differences that we will introduce in the following podcasts. Okay, so that's a quick run through equatorial waves, but as I said, there are podcasts on my course on tropical dynamics where we go through the details, and you can look those up. If you are not into those mathematical equations and the hairy solutions, then you can just pay attention to the wave number frequency diagram and can try to develop a intuitive sense for the physics of what we are trying to do here in this series of podcasts. Okay?